This is the second lecture which pertains to carbenes. You may recall in the last lecture we looked at the structure and stability of carbenes, and we also looked at the generation of carbenes. In other words, what are the reactions that will yield carbenes as an intermediate. In this lecture, we will concentrate primarily on the reactions of carbenes. Since we now know how to make carbenes, we will now concentrate on their reactions. Okay, the first reaction that we look at, or the type reaction that we look at, is addition reactions. This is an addition essentially to a double bond, which we have seen before with the Simmons-Smith reaction. So the addition of carbene to an alkene to form cyclopropane. But let's look at it in terms of a specific reaction and what should occur. The carbene can be described as a nucleophile. Remember, a nucleophile is a nucleus-loving species, or a species that has an unchaired pair of electrons. Another term that's often used is a Lewis base. So a nucleophile is nucleus loving, loves positive. In other words, phile here means loving, and nucleus, since it's positive, is positive loving. So this end of the carbene is in fact nucleophilic. This aspect of the carbene is actually electrophilic because it has an empty orbital. So let's analyze this term again. It's philic or phile, loving, and electro, which means electrons. Electrons are negative. So it's negative loving, or in other words, it's electrophilic. So the carbene is both nucleophilic and electrophilic. So we have here an alkene which has a pi bond here, which has 2 electrons. So one mechanism is that these electrons can go to this carbon, and the pi electrons here will now go to the vacant p orbital, and what we have here is a cyclopropane. So again, carbenes react with alkenes in an addition to the double bond to form cyclopropane, because they are both nucleophilic and electrophilic. Here is a little more details about that type of reaction. We have a transalkene, we have a singlet carbene, we have a transcyclopropane. This type reaction is called a stereospecific because it takes a specific stereoisomer as a reactant, and it gives a specific stereoisomer as the product, the trans. So it goes from trans to trans, and now this is. On the other hand, if it were a triplet carbene, and triplet carbenes behave as if they are diradicals. So as you can imagine, it would add first, and then there's possible rotation. So in other words, we'll have here the trans and the cis product. So it's not a stereospecific reaction here because you do not get a specific stereoisomer as the product. But for our study here, we're concentrating more on the singlet carbene, and it gives the trans, it's stereospecific. So if this were trans, it gives the trans, and if it were cis, as you'd expect, it would give the cis cyclopropane. Let us look at another type reaction. This reaction is called an insertion reaction. So it's going to be an insertion into a bond, specifically into the CH bond right here. So in theory, or a model for the reaction here, or hypothetical, is we have a CH bond with 2 electrons. Remember, each sigma bond has 2 electrons. This is electrophilic, as we just pointed out. So these electrons can come into the electrophilic region of the carbene, and the nucleophilic end of the carbene can go to this carbon. So as you see here, this is the carbene that's inserted into the CH bond. Here is a specific example. So we have here in light, we have the carbene that can be generated by the loss of nitrogen. You may recall that reaction. So it gives the carbene right here, and it can insert into this CH bond. CH bond here. So here is that carbon, same carbon. Here's that H, So you can see here the carbene has inserted itself right into the CH bond to form a new product here. Okay, let's look at some more. Here is another possibility for insertion. So here we're looking at the possible products. So here we have an alkene, cyclohexene. Pardon me, let me get rid of this. So here we have an alkene right here, cyclohexene to be specific. And of course this here gives here the CH2 carbene. One product, as you can expect, is right here because it's just adding right across. But let's look at the insertion. So we have here a hydrogen. So you can imagine the CH2 inserting right into this to get this product. We have another hydrogen over here, actually 2, but it will just insert into 1. So here we have the CH3 here because of that insertion into the CH bond. And we can imagine the same happening back here to give this. And of course back here would be the same as this one. So we get these as possible products. So again, you should be able to look at a potential reactant such as this, the carbene that's generated, and see the possible products. Notice light again is used to generate the carbene from that diazo compound. Another possibility here is a carbene, singlet carbene, can insert itself into this OH bond. So notice it's not a CH bond now, but it's an OH bond. So as you can see here, here is the O and the H, and here's a carbene that's inserted right into the OH bond. So again, an insertion into a bond, an intermolecular insertion because it's inter because we have 1 and 2 molecules reacting to form 1 over here. Let's look at the other one. The other type is an intra. So instead of an intermolecular insertion, this is an intra, which means within the same molecule. So let's look at this. So we have here a CH2 and an H. We're really a CH3, but I've drawn this out so you can see the H. Here is the carbene. It can react here, and then these electrons here from the sigma bond will migrate along with the hydrogen into the p orbital. So what we have over here is an alkene as a product. Notice this is neutral, so that's a final product, isolatable. So we have essentially a migration of the H to the carbene. Here's another example. This will be generated, or the carbene will be generated based on the loss of nitrogen here. So we can imagine here we have N2 coming off in the presence of light. So we have the carbene that's generated. It's nucleophilic and electrophilic. So the nucleophilic end can react with this carbon, and this can migrate over to the electrophilic end of the carbene. So you can see here is a double bond, and this actually migrates to give this type compound, a ketene type compound. So look out for that. It's possible to have an intramolecular insertion within the same molecule. Let's see the requirement for a 1-2 shift. Ideally, the group that's migrating from the one part of the molecule to the carbene, the dihedral angle here must be 0. As you can imagine, it must be right across from the p orbital so that it can just move right over into the p orbital. So that's ideal, but as you'll see, there are slight differences from this 0, but if it's close enough, the migration will occur. What you'll notice here is that the hydrogen has the greatest ability to migrate. Then next we have other groups such as the methyl and the phenyl. But for our study, more than likely we will concentrate primarily on the hydrogen migration. Let us look at this example here. So let's analyze this one carefully first before we see what's happening. So here we have the NNTS, the tosyl hydrazone. And remember, this hydrogen here is acidic. So we have this, which is a strong base, methyl lithium. Remember, whenever a carbon is bonded to a metal such as lithium or potassium or sodium, it creates a very basic carbon. So this is a very strong base. It will abstract this hydrogen, and as we have seen from the previous lecture, it will in fact liberate the nitrogen here and the tosyl group as a salt with the lithium. But the bottom line is we will create here our carbene right here. So this would be our carbene with the 2 groups bonded to it. After the reaction is done, what you will observe is 1 butene and 2 butene, cis and trans. Notice the 1 butene is low in percent yield, the trans is higher, and the cis is next in line. But the bottom line is the 2 is more prevalent compared to the 1 butene. Let's see what should happen here. So here we have this carbene. Carbene is right here. So I've just drawn it differently here. So we have the CH3. This is it. And the CH2. And the CH3 right here. So what we can have here is an insertion into this bond, which will give us the 1 butene. We can also have insertion into this bond, which will give us the 2-butene. As you can imagine, the 2-butene is higher in yield because it is more stable compared to the 1-butene. Remember, the more substitution around the carbon-carbon of the double bond, the more stable will be that alkene. So this has 2 hydrogens here and 1 hydrogen, so it's a monosubstituted alkene. This has here a hydrogen and a hydrogen, so it's a disubstituted alkene, more stable than a monosubstituted alkene. We also know that a transalkene is more stable than a cis-alkene, so that explains why the amount of cis-alkene is less than the transalkene here. Notice again that this does not migrate into this bond here, which does not result in a methyl migration. Does not result in a methyl migration. Why? Because the hydrogen migration is preferred over the methyl migration. So here is the products, or here are the products here, and here is the explanation of the products. Let's look at another type insertion. This time it's not the CH that is adjacent to the carbene. So here's our carbene. Here's a CH2. Here's a CH2, and here is the CH. So we can have a migration or an insertion into this bond where this H comes over here, and we have a bond here to form a cyclopropane if it's like this. If it's like this. So let's look at a specific example here. So we have seen this type hydrazone before, tassel hydrazone. And we know the strong base. Notice that's the strong base here, methoxide anion, or sodium methoxide, pulls off this proton here, and of course the electrons come in and go onto that. Eventually it comes back out, so we have nitrogen coming off, and we have the carbene right here. Once we have the carbene right there, it can now insert into that bond, and we have that as the product. So again, an insertion, but this time it's not a 1,2, but in this case it's a 1,3. You'll see later on that it's possible to have even migration further from the alkene center. This is another example here. So strong base, hydrazone, tassel hydrazone, acidic hydrogen. So what you'll expect is the carbene right here. After this comes off as nitrogen. So this is the carbene. It can insert into that CH. And here it is. So here's that carbene that's inserted into that CH. So that's this H is right here, and this H is right here. So we have an insertion into that. Let's look at this example here. Same type tassel. In this case we have light, creating nitrogen coming off. So we can expect the carbene to be right here. Let's see what should happen though. So here we have CH3s, H's, H's, and H's. And 1 H, well 3 H's. So you can see that this carbene can insert right in here to get that as a product. This carbene can insert into one of these H's, CH bonds here to get that as the product. Likewise, it can insert into one of these here, one of these CH's here, to get that as the product. As you can imagine, it could do here, but that's a highly strained four-membered ring, so highly unlikely to form because of the strain of the four-membered ring. So here are three possible products that are made based on the carbene that's formed right at this carbon. Here's another example. Light giving off this as nitrogen, so the carbene is formed right here. So again, here's an H and here's an H. This is right adjacent to it, so we can have here what is actually over here. Same thing. So we have here the alkene, but it's possible to go over here. So here we have an insertion, so we get this as a product. And of course, same thing can happen here. So we have that as a product. So you should be able to predict the products that are formed based on the carbene intermediate that's possible. Of course, you can expect a mechanism question of this type. Let's look at dialkyl carbons that cannot undergo hydrogen shift, or should we say do not undergo hydrogen shift. Here's a carbene. As you can imagine, there's no hydrogen here, and the hydrogens that are on this carbene are very much removed, and the geometry cannot be aligned for that migration. So this is the adamantane, adamantyled carbene, fairly stable, no migration, and it's been studied by different types spectroscopy. Same thing here, tert-butyl. So here's a tert-butyl right here, and a tert-butyl right here. No hydrogens on the adjacent carbon, and these hydrogens here are too far removed to get that exact geometry. Remember that dihedral angle should be 0, ideally 0 for the migration. So it does not happen. So this is the pretty stable carbene, the di-tert-butyl carbene. Let us look here at another type of reaction with a nucleophile. So here's a carbene, singlet carbene. Here is pyridine. It's nucleophilic because it has an unshared pair of electrons. So don't forget, a nucleophile has an unshared pair of electrons, at least one. So if these unshared pair of electrons go into the p orbital here, you can see that we do have this carbon here with a pair of electrons, and it's negative. You may recall from your general organic that a compound of this type is called a ylid. Why ylid? Because it has a carbon that has a negative charge and attached to a heteroatom. You may recall the ylid that we looked at in undergraduate is the one that's used to make the carbon-carbon double bond. So that's one where that's bonded to a phosphorus. So we have a phosphorus ylid for that. There are other type lead ylids, and they are sulfur, for example, sulfur ylid. But this particular one here is a nitrogen ylid because it's a positive nitrogen bonded to a negative carbon, and this carbon is nucleophilic. Let's look at another reaction. I think this is the last one for this lecture. So let's look at the reactions of a diazoketone or diazoketones in general. So here's the alpha diazoketone. Just to refresh your memory, the alpha here means the first. So here's the carbonyl. So the first carbon from the carbonyl is right here, alpha carbon, and it has the diazo group. You may recall this is the diazo group. Using resonance, we can put the charge onto the oxygen, and you will recall this looks like nitrogen right here. So when these electrons come back in, this kicks out as N2, and we have a carbene right here. That's a carbene. If the carbene in the the carbene can have migration from the group that's bonded to the carbonyl to the alpha carbon. So we have this, and these electrons come back in, and we form what's called a ketene. So again, so this actually migrates over to here, and these over to this carbon. Why? Because it has a vacant p orbital. The electrons, the unshared electrons of the carbene, then come back in to form here a double bond right here, and we have this functional group here is called a ketene. Very reactive in the presence of water, as you can imagine. Water will react right here, and we end up with the carboxylic acid. This rearrangement here is known as the Wolff rearrangement. As you know, in science, especially chemistry, we tend to associate different type reactions with the individual who discovered these reactions. And in this case, Wolff discovered this reaction, hence the name, the Wolff rearrangement. I think this is the last for this lecture. So this is the last for the lecture on carbenes. The emphasis here should be on reactions. Once we have made carbenes, what will they do? Remember that carbenes are intermediates. You can't go in the lab and isolate a carbene and put it in a bottle. They are intermediates onto different products. Here's a classic example. So we have the carbene, and it can react, it can undergo migration to form a ketene, which is a fairly stable molecule, but it's a molecule as a product. And see. So continue studying hard, continue reading this chapter in your book, and in the next lecture we will start carbocations. That's a positive species, and we'll discuss the synthesis, the usual stability, the synthesis, and of course reactions. Okay?